Welcome, everyone. It is absolutely fantastic to be here with all of you at the ICITL conference in beautiful Oslo. I'm just thrilled to be in a room full of international researchers, tech educators, and innovators. As the primary author, representing an incredibly dedicated research team from both the National Yunlin University of Science and Technology and Universitas Negeri Semarang, I'm super excited to share this explainer of our latest research with you. Today, we're unpacking a real breakthrough in how we elevate vocational education using multimedia. Specifically, we're going to look at how folding video into project-based learning completely flips the script on how students pick up complex, hands-on skills. We've basically taken our published paper on multilevel turning and distilled it right down into this explainer for you. So let's get into it. All right, here is our quick roadmap for today. We'll start with the Vocational Training Challenge, move into designing video-assisted PjBL, break down our experimental methodology, analyze the student outcomes, and finally, look at the future of tech education.
Part 1. The Vocational Training Challenge.
So here's the question that literally kept our team up at night. How in the world do we bridge the gap between theory and practice when it comes to complex machining? Competency-based education is all about hands-on skills. We're trying to get these students ready for the actual job market. But mastering something as precise and, let's be honest, as intimidating as multi-level turning on a lathe machine, that is tough. You've got students moving straight from textbook theory to operating heavy, complex physical machinery. And in a normal classroom, instructors just can't be everywhere at once. They can't give real-time, one-on-one supervision to 20 students at the same time. The result is that students often disengage, or they just don't get enough guided practice. So the big puzzle we had to solve was this. How do we give them that essential, personalized, experiential learning without sacrificing safety or academic rigor?
Which brings us to Section 2, Designing Video-Assisted PjBL.
Normally, students get one live demonstration from the teacher, right? And if they blink, they miss it. Instead of relying on that, our video project-based learning system, VPjBL, bakes step-by-step video tutorials right into the learning module itself. It's got interactive pause points and guiding questions built right into the timeline, which completely opens the door for self-regulated learning. So if a student suddenly forgets step 4 of multi-level turning, they aren't just standing around waiting for the teacher to be free. They can instantly pull up the exact complex procedure right at their own workstation. It's built around 3 core parts: a clear intro with objectives, a real-world demo of the machining, and a reflection phase so the student can actually review their own work.
Now, I want to be clear, we didn't just throw videos on a screen for the sake of using technology. This is heavily grounded in academic theory, specifically Richard Mayer's cognitive theory of multimedia learning. Think about it. Complex machining throws a massive cognitive load at a novice. By using video, we're tapping into the modality principle, syncing up the visual and auditory channels so they perfectly align with the physical task. Plus, by breaking the turning process down into digestible chunks, what cognitive scientists call segmenting, we actively prevent cognitive overload. The students are building their mental map, their schema, one step at a time. It beautifully marries the active problem-solving of project-based learning with the absolute cognitive efficiency of multimedia scaffolding.
Section 3, our experimental methodology. Let's look at how we tested this.
So once we had the theoretical framework dialed in, we had to see if it actually worked in the real world. We set up a quasi-experimental study with 66 mechanical engineering students at a public vocational high school in Indonesia. We kept them in their intact, normal classes just to make sure we didn't disrupt the school schedule. Both groups had the same academic backgrounds and the exact same prior machining experience. Our control group, which had 34 students, did traditional project-based learning. Printed modules, standard teacher explanations, you know the drill. Our experimental group, with 32 students, got the intervention, project-based learning fueled by our instructional video support system. And crucially, both groups had the exact same teacher using identical lesson plans. It was a perfectly fair, level playing field.
Here is how that actually played out over 5 weeks. Week 1, we gave all 66 students a practical competency pre-test just to lock in their baseline skills in multi-level turning. Week 2, we introduced the learning activities. Then, the fun part, weeks 3 and 4, they got on the lathes. Their goal was to produce a physical workpiece, matching exact dimensions on a job sheet. The control group used printouts. The experimental group used our video system. Finally, in week 5, everybody took the practical post-test. We graded their final physical workpieces on a super strict validated rubric that looked at their preparation, their method, the final results, their attitude, and their time management.
Okay, Section 4, Analyzing the Student Outcomes. This is where it gets really exciting.
Check out these numbers. In the pretest, both groups started pretty much neck and neck, 58.03 for the control group and 56.56 for the experimental group. But then, look at the post-test. The control group went up to 70.09. That's a solid, expected bump for traditional project-based learning. But our experimental group, they skyrocketed to an average score of 87.66. No joke. We ran an independent t-test and hit a t-value of 41.450 with a p-value of less than 0.001. So statistically, highly significant. The intervention absolutely worked. But honestly, it gets better. Beyond just the p-value, we ran Cohen's d to see the practical effect size of what we did. The result, 1.732. Now, for the stats folks in the room, you know that is a massive effect size. But I want to frame this practically for a second. That 1.732 isn't just a math stat. It represents a real human impact. It's the difference between a vocational student standing in front of a loud, spinning lathe feeling overwhelmed and hesitant versus a student feeling totally empowered, self-directed, and confident enough to craft a precise physical object. It's a real game changer.
We also ran an N-gain analysis, which basically looks at the actual learning improvement compared to the maximum improvement possible. Our control group hit an average N-gain of 0.2859, which is considered a low to medium improvement. Meanwhile, the experimental group hit an average of 0.7155. That rockets them straight into the high category of learning gain. What this tells us, for sure, is that when you combine hands-on, project-based tasks with visual multimedia scaffolding, the depth at which students acquire technical skills just goes through the roof.
But, we had to ask, did the students actually like using it? The answer was overwhelmingly yes. Based on a validated questionnaire, exactly half, 50%, rated the video experience as very good, and another 43.75% said it was good. So you've got nearly 94% of the experimental group giving this a major thumbs up. In their comments, they specifically mentioned that having the visual demos cleared up all the tricky steps, it boosted their confidence before they even touched the machine, and it let them learn at their own pace without feeling left behind. Finally, Section 5, the future of tech education.
So, bringing this all together, what's the big takeaway for us as educators and researchers? It's that cognitive and multimedia theories have incredible measurable power in real-world vocational spaces. This data proves that video project-based learning significantly amps up practical competency. And it works because it directly targets and reduces cognitive overload when students are doing complex tasks. Plus, it totally changes the vibe of the classroom. It promotes real learner autonomy because students aren't bottlenecked waiting for a teacher to come over and help. Ultimately, it bridges that really frustrating gap between what they read in a book and what they can actually execute on the shop floor.
As we look to the future, we have to acknowledge that modern industry moves fast, and it demands workers who can learn complex skills independently. If we're going to prepare our students for that reality, the way we design instruction has to evolve right alongside it. So I want to leave all of my fellow ICIL attendees with a thought to chew on. Now that you've seen the massive effect size that video scaffolding can have on practical competency, how will you integrate this kind of multimedia into your own vocational curricula? Thank you so much for your time today. It's been an absolute pleasure, and I'd love to open the floor to any questions you might have.